Last talk of the second week. It's a pleasure to have Jan tell us about Pions.
Thank you, Pedro. So hi, and thank you all for making it to the last talk of the week. So today I'll be talking about this thing. I know there's the title, it's a little confusing. Bootstrapping Pions in currents at large N. And this is based on a very recent paper that appeared 2 nights ago on the archive with Leonardo Rastelli. So this is basically a second step in a program that we're pursuing of bootstrapping confining gauge theories in the large N limit. And last year in Portugal, you may remember that I talked about something very related. That was the first step. That was bootstrapping Pions at large N. So the basic idea is we're bootstrapping confining gauge theories, and we did it by putting constraints on the scattering of Pions. And today we'll see how we can upgrade those constraints by including conserved currents into the system. Okay, so I'll first review a little bit the general program. I'll talk a bit about the bands that we obtain with just pure Pion scattering, and then we'll get to the new results. Okay, so the basic idea of this program is that at some relatively high energy scale, we have some confining gauge theory. Which may have some description in terms of gauge fields and fermions and whatnot, but it confines and therefore it admits some description in terms of all its bound states. So we should think of it as parameterizing these confining gauge theories by an infinite collection of all the masses of the bound states and their on-shell coupling constants. So this description of confining gauge theories is very well qualitatively similar to the CFT data, where we would have scaling dimensions and OPE coefficients. So this calls for some bootstrap analysis of these theories. And the question is, can we bootstrap them? Can we explore put constraints on these parameters and find perhaps some theories of interest in some interesting corners of plots in this parameter space? Now, the bootstrap problem would be we take all the scattering of all these mesons or bound states in this theory, and then we demand crossing and unitarity, and we use that to constrain these things. And we have to start with one of these processes, so we'll start with the scattering of the lightest states. So this is the whole collection. We'll start with the lightest states. And since we're studying the scattering of lightest states, then it's better to use another language, which is the language of effective field theory. So the picture is that we integrate out all the heavy mesons, heavy particles in the spectrum, and we let the theory flow to the IR, or we have some effective field theory for the lightest excitation. Let me call it 5 for now. It doesn't have to be a scalar. Okay, so now in this new description, all this information is encoded in the Wilson coefficients of the EFT, and then bootstrapping these things is the same as carving out the space of valid or healthy effective field theories in this language. Okay, so right, there's one assumption that we make to make this setup sharp, which is that we take the large N limit. So we think of some SUN gauge theory or so, we send n to infinity in Tufts limit, and what that does for us is that the EFT then becomes weakly coupled. And that's in this regime is where the methods that we will use that are positivity bounds become sharpest, because there's no loops and everything is rigorous. So okay, the target. So this is the general program, and the target, of course, that we have in mind is large N QCD. So this will carve out. Well, there's many theories that satisfy these assumptions, but the target would be large N QCD. Yes.
Can there be higher point couplings?
Yes, that's a very good question. So in general, yes, I was being schematic here, but if you have suitable, so the high energy behavior, so if you have a good enough Reggie behavior, so if you could write down and subtract the dispersion relations, this would be enough. In general, we will need the lowest derivative for point couplings, but here I was being more schematic, trying to not. But so yes, in principle, a finite number of on-shell higher point couplings you would need. Thank you for the question. Yeah. So right, so large N QCD, it's basically a theory, SUN Yang-Mills theory with NF Dirac fermions that we'll take to be massless. So this is the chiral limit, and we'll do that for simplicity, though this assumption could be lifted. And then the symmetry of this theory has a symmetry that's U and F left times U and F right, which is spontaneously broken to UNF vector or diagonal. You may be confused. Well, it may look a bit surprising because usually people talk about SUN, and the U1 axial here is not included. But at large n, when we send this n to infinity, this anomaly. Okay, so this is broken by a 't Hooft anomaly, but at large n, this anomaly is suppressed, and then the corresponding Goldstone boson, which is the eta prime, becomes massless. So if you do the counting, you see that in this spontaneous symmetry breaking, we have NF squared Goldstone bosons, which are the pions. Okay, so why am I reviewing all this? Because now we see that for large NQCD, the lattice states, so this phi here, will be nothing but the pions, which are massless Goldstone bosons. Okay, so the problem, in order to find large NQCD, is to put constraints on pion scattering. Now, of course, that's, there's other theories that satisfy these assumptions, and then we'll try to keep inputting more and more information of QCD to try to single out QCD. Okay, so, right. So the effective field theory for pions, I've written here. It's the famous chiral Lagrangian. And for now, let's look just at the black terms. So this one's over here. We'll talk about the other ones later. And we have a nonlinear sigma model with this U matrix. That's a matrix valued in the coset space UNF. And we have the pion here and the generators of the algebra. So what we write is all the possible terms compatible with the symmetries in an expansion of derivatives with the unfixed coefficients. So these kappa 1, kappa 2, and even f pi, and the higher terms are the Wilson coefficients, which encode all this information of the spectrum. Okay, so now the strategies, we study 2 to 2 pion scattering. So pi, 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 pi. And then I'll review a little bit in more detail how this is done, but by writing down dispersion relations, obtaining some rules and null constraints, we can start carving out the space of couplings. And this was one of the main results that we obtained by doing that. So here I'm plotting a two-dimensional slice of this infinite dimensional space of Wilson coefficients, where I have, it's some linear combination of this kappa 1, kappa 2 that I call G2 tilde and G2 prime tilde. Okay. Importantly, we can only bound ratios of these coefficients because when we take the large n limit, all of these couplings are suppressed by 1 over n. So all of these are proportional to 1 over n. So the only thing that we can access are really ratios of these guys. Okay, this will be important later. So this was the result that we found, and this region here is the loud region. So all effective field theories that are compatible with healthy UV completions must lie inside this space. Okay, so this has a bunch of corners, and we'd like to understand what they are. And for these 3 corners over here, we understood them in terms of very simple solutions to crossing. So like a simple scalar exchange or some funny solutions. But there remained this point over here that was a kink. And the question was, could this be a large NQCD? Large NQCD. So we didn't manage to explain this point with simple solutions to crossing. The best we could do was explain part of this line with a single spin-1 exchange. So this thing, if you compute a single J equals 1 exchange, that would be the exchange of a rho meson. One has to be completed with stuff at infinity, and that would explain some part of this bound. But there was a mismatch here from the numerical king to this point over there. Okay. Then there was another nice paper later last year by Fernandez, Pomarol, Riva, and Ciotti, where they argued with some analytic methods that once we include enough null constraints and numerical, more and more constraints, this king will very slowly converge down to this point over here. So the current status of this plot is that many of the corners are explained by simple solutions to crossing, but not everything is known, because for instance, interpolation between this point over there is still not very, there's a very naive interpolation you can do, but there's some examples that lie right outside this band. So it's not fully understood what's the features of this plot. Yes?
Simple question about dimensions of coupling. So
right.
These kappas, they are dimensionless?
No, they are dimensionful. Yes, I think I've neglected all the powers of the mass. So yes, sorry. I believe I need m squared, m rho squared. Let's see. I think I need m rho squared here, m rho squared here. Does that look good? Yeah. So yes, these are dimensionful.
I also have a question. So so these couplings are 1 over n effect, you said, and the mass of the eta prime is 1 over n effect. Why do you not include the mass of eta prime? Would it be interesting to do it in this framework? Or?
No, it's subleading. So yeah, if you do the counting right, so yes, I understand the question, but yeah, once you do the coupling right, at leading order in these interactions, you can treat the eta prime as massless. So that's an effect that comes later. There's something we could do that instead of taking the 2th large n limit, we could take the Veneziano limit, where we have NF and we keep the ratio of NF and N fixed, and that would give a mass to the eta prime. But for now, we're keeping this fixed, and then we send this to infinity, and then it becomes massless, even at leading order in large n. Any other questions? Okay. So where was I? Yeah, so the question is that we don't really know where QCD is. It could be in a boundary, it could be well inside the bulk. So what we would like to do now is push this program forward and see, try to input as much information of QCD into the Bootstrap problem. So here I want to review a little bit how much we told that story that we were looking for QCD, or is this just the most general thing we could do for scalar scattering? And there's basically 3 things that I want to mention that some of them we did manage to input, some of them we did not. So the first one is Zweig rule. So Zweig's rule is just a statement that at large n, all the resonance, so all the scattering amplitudes are meromorphic, and all the exchanges that you can have correspond to physical mesons in the spectrum. So large n, the only thing you should exchange are pure QQ bar bound states. And then this had some conditions on the isospin and ended up meaning that this amplitude could have no T-channel poles. So that's something that we inputted and gave some of these bands here were due to that constraint. So that's something that goes beyond the most general scattering process. Then the other thing that we inputted was spin 1 Regge behavior. So spin 1 Regge behavior. So generally, for any scattering process like this, in order to write down dispersion relations, you'll need a number of subtractions, and you're usually guaranteed a spin 2 Regge behavior by Froissart bound from unitarity and causality. But in this case, in the large n limit, this Regge behavior, I'll review that later, is controlled by the leading Regge trajectory, which is that of the rho meson. And then that allows us to have further subtractions. And if we didn't impose this, we wouldn't even be able to make this plot, because that's how we access this f pi, and we can use it to normalize. So that's the second thing that we inputted that goes beyond the most general scattering process. And then the last thing that we would have liked to input, but we did not, that we could not, was Adler 0. So the Adler 0 is just the statement that these pions are Goldstone bosons and that they are derivatively coupled. So if you take that amplitude and you expand it at low energies, it starts with a big 0 here, that's the Adler 0, and then it starts with non-zero coupling, G1, S plus U, and so on. So in general, you could have some constant here, but for pions, this should be a 0. And we'd like to input that in the problem, but since we're using a spin-1 Regge behavior, this is too low, and we cannot access it with dispersion relations. Okay, so these are the 3 ingredients, and we would like, we'll see what we can do to push these things farther. Okay, so a clear future direction that we could use is to go back to this parameterization here and start considering not just the scattering of pions, but pions and excited mesons. That could be the rho meson. That's actually the subject of ongoing work in collaboration with Johan Henriksen and Alessandra Vicky, but that's not what I'll talk about today. Instead, today we'll include conserved currents into the system. So we'll not just use scattering of pions, but we will consider scattering of pions and probe photons that account for conserved currents. Okay? And just as a teaser of what we're going to find, we'll see that all these 3 things get extended, and with this bigger system, we can input a lot more about QCD into the Bootstrap. So Zweig rule will get generalized.
Can I ask a question about this the 0?
Yes.
So if you were to do non-perturbative Bootstrap, so without large n limit,
yes,
then would this problem also exist there?
The Adler zero?
Yeah, I mean the fact that it's difficult to access.
I believe you could access it in that case because you don't write down. I'm not an expert. You don't write down dispersion relations. You just have some answers, and I believe you could input that this thing has to be zero. But that would be, as you say, a subleading order.
But I thought that in the non-perturbative method, it's extremely hard to do massless external states. No.
Well, they did gravitons.
Pions is hard.
I mean, they did Brannons.
No, it's easy. Because they are
But you had a mass.
The numerics become a bit harder than massive, but we did it, and I think Dennis, Vitaly, and Kellen are doing it good. Yeah, not Andrea.
Yeah. So. Right, so yeah, I believe you could input that, but that would be subleading in N, and we'll see that large N for us it's all over the place because it simplifies kinematics. It allows us to do this Zweig rule and things like that. Okay, so as I was saying, in this bigger system, these things will get upgraded. The Zweig's rules will get upgraded to large N, what we call large N selection rules. Which in particular impose this, but for more general systems, it imposes further constraints. Then the spin-born Regge behavior, we'll see that we can input in many different processes, but actually in some particular combinations, we can input information about the subleading trajectory in what we call improved Regge channels. And then finally, we'll see that Adler zero generalizes in this bigger system to a lot more Goldstone constraints. So constraints that come from the fact that these pions are Goldstone bosons. So the Adler zero we won't manage to input, but there's analogous things that generalize this condition that we will be able to input. These are Goldstone constraints. Right. So yeah, I'll also discuss some abstractions that seem to be numerical abstractions, but I'll do that later. So are there any questions so far? Yes, question over there.
So, can you say something about whether one expects this large N QCD theory to be isolated? I mean, at least naively, you can add extra massive quarks.
Right. Yeah, so I don't think it'll be isolated, and that's why by just imposing crossing and unitarity, we don't find any island or anything like that. But that's why we want to start inputting more and more information. That if we input enough information about QCD, we might be able to isolate it. For instance, we'll see that with this we can access the anomaly, the chiral anomaly, and that's something that would separate into disconnected sections if we've managed to input it. Like there's some quantitative information of QCD that we could input. So yeah, the hope is that we need to be clever and start inputting more and more assumptions to try to separate it.
So in particular, that would get rid of the possibility of having extra massive quarks?
Right, that would change the anomaly, yes. But we'll see that there's some subtleties that, yeah, I'll get to it later. But yes, thank you. Anything else? Okay, so, right. So I think, yeah, I've said all I wanted to say, general motivations, and now we can get to what we actually do. So a very schematic outline of what I'm going to do is to answer the following questions. First, why is this a good system to probe these things? And I'll give some preliminary motivations. Then how do we do this problem? Because we'll see that it actually turns out to be quite technically involved. And I'll spare you most of the details, but I'll try to give you a flavor of the machinery we've had to develop. And then we'll see what we get. I'll discuss some of the plots, not all of them. And then in the end, I'll discuss so what? What do we do with this? And what can we do to go beyond this? Okay, so let's start. Right, so as I was saying before, QCD has this global symmetry that's spontaneously broken to this other one. And what we can do is to consider conserved currents associated to this global symmetry. So we could have correlators, not just of pions, but of pions and conserved currents that we have most generally, the left current and the right current. And then in order to probe correlators of these conserved currents, what we have to do, it's very simple. We couple the action to background gauge fields, a left and a right. And then we can take variations with respect to these background gauge fields to bring down conserved currents or another current into these correlators. Okay, so this is the most general thing we could do, but it's quite complicated. So for simplicity, we'll restrict to a particular background, and not just for simplicity, but also for its physical implications or phenomenological implications. We'll restrict to an electromagnetic background. So we'll only consider electromagnetic currents in the broad sense of the word that I'll describe in a second. So there are just some U1 subgroup of all this group. Okay, so we'll take some U1 subgroup of U and F vector that we'll label by some charge matrix Q. Okay, and this corresponds to the background where A left mu equals A right mu equals some gauge coupling E, charge matrix Q that I'll give an example in a second, and then the U1 electromagnetic field, if you wish. Okay, so this charge matrix Q in the real world, when we have NF equals to 3, so that we have the up, down, and strange quarks, is taken to be this diagonal matrix that is Q equals 2/3 minus 1/3 minus 1/3, that some of you may recognize as the charges of the up, down, and strange quarks. Okay, but most generally we can take any diagonal matrix, NF by NF matrix, that it's basically valued in the Cartan subalgebra of this thing, and none of the results will depend. So Q is just some diagonal matrix that describes the charges. Okay, so this is the only background that we'll consider, and then variations of this will give us insertions of the electromagnetic current. Okay, so what do we have to do? So we have to do is come back here to this chiral Lagrangian, this effective field theory, and we need to couple this to background gauge fields. So I'll couple this to this background electromagnetic field, and in order to do this, all we have to do is promote the derivatives to covariant derivatives. I won't do it for all of them, but you get the idea. D, where this covariant derivative uses this electromagnetic field. Okay, D, and I would do it for all of them. But then in addition, I can add curvature terms that I've written here to save some time, which are terms that are proportional to the field strength. So this F mu nu is the field strength, so it vanishes when I turn the coupling to, it vanishes when I turn the electromagnetic and the background gauge fields to 0, but it actually is important when I want to consider correlations of currents. Okay, so these terms come with new additional Wilson coefficients that do not appear in pure pion scattering, but that will appear now in pion conserved current scattering or correlators. Okay, so in order to make sense of this. Yeah, in order to probe these correlators, what we're going to do is to think of these background gauge fields as dynamical fields that are very weakly coupled. So these we weakly gauge these gauge fields. So this E we keep very small, and then we'll consider scattering. So this is like an effective action for the interactions of pions and photons, which are the quanta of this guy here. Okay, so what we'll do is consider scattering not just of pions, but of probed photons. So we'll have stuff like this, pi gamma, and many other processes. Okay, but importantly, these photons are probe photons because they're just avatars for these electromagnetic currents. Okay, and in particular, that means that we could take them off shell, but for simplicity and again for physical relevance, we'll take them to be on shell as a first thing to do. Okay, so so one of the motivations for studying this process is that we can capture now these coefficients, and these coefficients capture informations of sectors in the spectrum that completely decouple from pion scattering. So we'll be able to probe mesons that did not show up in 2-to-2 pion scattering. And then the other motivation is the chiral anomaly. So I guess I can do it here. So, okay, if we look carefully at this effective action, and we expand it in pions and photon fields, we'll see that it doesn't capture all the processes that we observe in nature. Okay, and one in particular is the one driven or induced by the chiral anomaly. So the chiral anomaly is just the triangle diagram between two photons and an axial current. So axial current is just J left minus J right. And this is something we can compute. This is a quark running around the loop. We can compute with the UV QCD Lagrangian. Okay, But now this is a Tooth anomaly, so it must be matched under RG flow. And that means that in this EFT of pions, there must be some term that captures this anomaly. And the way to see this is just that we remember that the axial current is the current for a spontaneously broken symmetry. So when it acts in the vacuum, it actually generates some pion state. So we see that this thing will induce some effective interaction of two pions, a pion and two photons, okay? Now, we come back here, we don't see such interaction, and the reason is because we were missing some terms. And that term is the Wess-Amino term. So the Wess-Amino term, this is a parenthesis, is this big term over here that you can write as an integral over a 5-dimensional auxiliary manifold, if you wish, but it only gives you interactions for the 4D. So we would live on the 4D boundary of this manifold. And the reason why I hadn't discussed it so far is because if you expand it in pion fields, you see that the first contribution is at order 5 pions. So it only contributes to 5 points scattering of pions. And that's, be great to probe this. So yeah, this comes with a coefficient that's quantized, but otherwise unfixed. So this would be, again, some other Wilson coefficient. It would be great to probe this, but we would need 5-point bootstrap. And so far, it's not been developed. So we're, for the time being, we're constrained to doing 2-to-2 pion scattering. So this we cannot probe. But we'll see that indirectly, by considering this system of pions and photons, as you can see from there, we'll be able to capture this coefficient. Okay, so how is that? Well, you just have to couple the Wess-Amino-Wheaton term to this background gauge field, and you do that by adding a bunch of terms. So there's a closed form expression, but the only two I want to draw your attention to are these two terms. The first term has pi f wedge f, and it's precisely that coupling over there. And then the other one that will also be interesting is a contact interaction between 3 pions and 1 photon. And then you have higher couplings. Okay? And these come with coefficients that are fixed by gauge invariance. There's some fixed number that we know, and k, which this k being the same constant here in front of the Wess-Amino term. Okay? So now by matching the anomaly, you can compute this diagram, and then you match it to this coupling over here. You can fix that k has to be equal to n. N being what we send to infinity. Okay? So the number of colors in QCD. So, okay, why is this interesting? Well, because we're going to treat these couplings here as just some other effective couplings in the theory of pions and photons. So this we'll call achiral to remember that it comes from the anomaly. This we'll call bichiral, including the K. And then we'll put bounds on ratios of these guys with other couplings in the. We'll first ignore that this comes from any anomaly. We'll put bounds on ratios of this, and then afterwards we'll bring in the fact that we can fix these coefficients by matching the anomaly, and that will bring the n dependence explicitly into the game. So now all the bounds, as I was saying, cancel the n dependence, but now we'll be able to change some of these couplings, the ones that involve the anomaly, to bring in the n dependence. Okay, so now we can probe the coefficient of how things scale with n in these ratios. Okay, and any questions so far? So, right. Yes.
Yeah, this is a very important point, but I'm not sure I got it completely. So now you have n dependence. So what does it mean? You can tell n equal 100 from n equal 1,000. What exactly is going to happen?
No. Yeah, let me be more clear.
Yeah.
So, right. As I was saying, all these couplings scale with n, and yeah. 1 second. Right. So in particular, we can. Okay. So you have some coupling, G, that scales like some constant, and then n. Okay. So okay. Let me do an example. Yeah. So f pi squared is known to scale like n. And that means that as you send n to infinity, it tends to some constant times n. Now, what I'm saying, so far, we could not probe. I'm sorry? Yes. Yes. So yeah, this takes care of the dimensional analysis, and this tells you how it scales with n. So now the point is that now by bringing in the n dependence explicitly, we can probe these coefficients. Not in every case, only in cases where when we can capture the anomaly. But now this is very interesting because in lattice studies, they can They can precisely measure this quantity. So they can do studies for different n's, and then they extrapolate as n goes to infinity, and then they can see how f pi scales with n, meaning this coefficient here as you take n to infinity. So it would be very nice if we could do that. We're not quite there yet. I'll discuss how we may be able to get precisely this one, but that'd be very nice to compare to the lattice, because that would be a large n comparison, not just with the real world.
Okay.
Thank you. Anything else? Yes, over there. I can repeat the question if you want. Yeah. I'll when I describe, yeah. So, oh, sorry, I did forget. Yes, thank you. So he was asking that so far I've not used the large n assumption. Everything seems very general, but I've basically hidden some things. So for instance, this Lagrangian already has the large n assumption here because I only have single traces. More generically, you could have products of traces, and that's something that disappears in the large n. So large n is hidden here, and then we'll see later that when we start parameterizing things, I'll keep using large n every time. So it's hard to tell exactly what is large n, what not, because everything is large n, everything that I'm saying. So yes, many things will be true, all this matching of the anomaly and so on at finite n, but everything that I'll be doing, all the formulas that I write are true or correct at large n. Okay, thank you for the question. So, okay. Right, so yeah, so the diagrams, so these two couplings, just to emphasize how we'll capture them, this is a 3-point coupling, so it will appear in the 2-to-2 scattering of photons where they exchange a pion. Okay, this will be proportional to a chiral squared, and then this thing will be will appear as some contact term in 3 pions and 1 photon. Okay, so what we want to do is study the whole mixed system of scattering between photons and pions. And that's actually non-trivial. So let's get to it. Okay, so in order to use positivity, or unitarity and particular positivity, we'll need to consider the full mixed system, because this thing does not have is not closed under positivity, right? So we need to consider many processes. So we have pi going to pi, which we already did. We have 2 photons going to 2 photons, which many people in the audience have studied already. Then we have pi gamma to pi gamma, and in addition we have the interesting one for that one, which is pi to pi gamma, and of course crossing versions of like cross versions of this thing. The remaining 3 gammas and 1 pion is dead by, is not compatible with charge conjugation symmetry, so that doesn't appear. There's only these 4 processes. Okay, and the question is how do we do this? Right, so that point over there. Okay, so I'll quickly review how the story went for pions, and then I'll outline what are the differences that we have to deal in these cases, because otherwise it becomes very, very technically involved, and I don't want to get into all the details. Okay, so I'll build a flow chart of what's the steps that we have to follow. So the first one is we need to parameterize the amplitude. So parameterize. So by parameterizing the amplitude, I mean we have to deal with the flavor dependence of these pions. So A, B, C, D, these pions have some flavor dependence, we need to deal with that. So at large n, we remember this.
Just to speak English, is it clear that the gauge coupling is going to scale, the gauge coupling is infinitesimal, so it has to scale out of this analysis? Like,
yes.
It's clear?
It is, well, might not be clear from here, but what we'll build is some spectral density that, okay, so this is a system of mixed correlators, so in this will, positivity will be schematically 4 pions, 4 photons, 2 pions, 2 photons, and then you can also have the off-diagonal things. But you see here, this will scale like, so everything that we do will be doubly homogeneous in the rescalings of the pion and of the photons. So this E is basically the overall normalization of the photons, right. But there's also the overall normalization of the pions that we fixed here. So everything has to be invariant under both, and we'll see that things that are off diagonal are both, have 2 powers of the pion normalization, 2 powers of the gamma. Okay. So yes, everything is okay. Invariant. Thank you. Now, right, so for 4 pions, here we use the large n assumption. That's to remind ourselves that only diagrams with the topology of a disk contribute, where we have 4 pions inserted around the along the boundary, which okay, so we have a quark loop running around, and in the language of string theory, this would look like the scattering of open strings. So we have pi a, pi b, pi c, pi d. And this means that all the flavor dependence, large n, will be a single trace. So this will be proportional to trace of the generators, Ta, Tb, Td, Tc, as you run around the loop, times some amplitude that only depends on the Mendelssohn invariance, as in U. Okay? So this is the one that we will be probing. So after the parameterization, what we get is some amplitude that only depends on the Mendelssohn invariance. Okay? Now, once we have this, we have to study two regimes of this amplitude. One is high energies, and then the other one is low energies. So at low energies, what we do is expand this around 0. We have some Taylor expansion, as in U, and that has some G1, S plus U, ... And these coefficients correspond, are in one-to-one correspondence with these Wilson coefficients. Now, at high energies, on the other hand, what we use is the partial wave expansion. So this was the FT. The partial wave expansion looks schematically something like this. Imaginary part of our amplitude is some sum over spins of the spectral density that carries, takes care of the poles and singularities, there are only poles at large n, times some polynomials that are the Legendre or Gegenbauer polynomials, cosine theta. Okay, once we have these two ingredients, all we do is write down dispersion relations that link the high energies to the low energies. So dispersion relations. That it looks something like this. An integral around infinity of S of M SU with suitable subtractions equals 0. Now we shrink this contour, links low energies to high energies. We obtain some rules for these guys, null constraints from crossing, and then we can run the machinery of positivity bounds to derive that sort of plots. Okay? So now what we have to do is the same thing, but for all these processes. And there's one subtlety, or not subtlety, but that's one complication, that's that these guys depend on some polarizations or helicities of these photons. Okay, so to deal with the flavor dependence, we do the same thing. We draw all of these at large n will have contributions with the topology of the disk, but now the insertions won't be just pions, but also photons. And the photons here insert, instead of a generator, some charge matrix Q. There was this charge matrix Q here. Okay, so we deal with the flavor dependence in this way, but then we have to deal. So this will be proportional to some trace of some generator, some Q, and whatever are the other insertions. But now it will have, if we have a Q, now this will depend on some helicity, say a helicity of the particle 2, apart from the Mendelssohn invariance. So what we want is to use functions that only depend on the Mendelssohn invariance, as in U, but we have to deal with this polarization. And here there's different ways to proceed. So one way that has been used in the past, and that works very well, is to go to the center of mass and then consider the different amplitudes. So helicity plus, helicity minus, and all the possible combinations that are independent. Okay. However, for us it will be more convenient to work covariantly, meaning that we'll look for all the possible structures that take care. Okay. So we'll expand these in tensor structures that carry away this polarization dependence. So schematically, we'll have some mu depending on, say, lambda 1, lambda 2. As an example, we'll expand this as some sum over tensor structures of something like this. So EI, lambda 1, lambda 2. So we construct tensors, invariant tensors that carry, that depend on the polarization vectors, mu, and momenta, and then we expand in this way so that the coefficient now is a function that only depends on S and U, which is the one we will use. And when you work, the reason why we work covariantly is that perhaps here is not super interesting or super necessary, but when you start including masses and things like that we are going to the next, crossing becomes very it's very apparent in this formalism, and not so apparent when you start when you evaluate things in the center of mass. So in any case, we do this expansion. You have to be careful whether they are independent or not, but you can look carefully what are the independent structures. And then in the end, what we obtain is a bunch of functions with reduced amplitudes, as we call them, that only depend on the Mendelssohn invariance. Okay. So what we do after this parameterization is to obtain a collection of these amplitudes. And just so you get an idea of how complicated, the system becomes, I'll do the counting quickly of the number of functions we get. And number of functions for each process. So for pions, we saw there's only one function. This is m as in u with some crossing properties that we know. For 4 photons, as many people here know, there's 3 functions. With some of them are fully crossing symmetric, some of them are just SU symmetric. For 2 pions and 2 photons, there's 4 independent functions, and then for 3 pions and 1 photon, there's again just 1. So if I did the counting correctly, there's a total of 9 independent functions that we have here. Okay, so yes.
Did you have to consider also the pi to pi gamma, since kappa is already in gamma gamma to gamma gamma? I mean, you have 2 terms. Is it mandatory to use both?
Pi to pi gamma, this one here?
Yeah, so since kappa also appears in the other term that is in gamma gamma to gamma gamma, right? You drew 2 diagrams.
Yes.
So you're considering both to get more constraints, or it's mandatory to consider also this?
Very good question. So at first we were like, oh, maybe you don't need this. This is enough because already captures the anomaly. But for some reasons that I'll explain later, it turns out that we're unlucky. And this coupling here, while we write a sum rule for it, it decouples from all the positivity bounds. So we got very confused. But in the end, we understand what's the reason. I'll discuss that in the end. But then this doesn't happen for this one. And that's why it's mandatory to, if you want to get some results, it's mandatory to look at this one because this one does couple to results. And what we'll actually find is that we can extend this plot in a third direction where we bound this big chiral here. Okay, that's why I emphasize this one here, because it's the one that we can, at this stage, give results for. Okay, thank you for the question. So, okay, let's recap where we are. So we have this flow chart. We need to parameterize the amplitudes. Then we need these 2 regimes, and then we'll write down dispersion relations. And what we've done so far is have the whole problem encoded in 9 independent functions with known crossing properties. So now, for each of them, the low energy is very easy. We just do this expansion for each of them, m sub I, some couplings that will be different in each of them, and that we can get, they're related to all these couplings. Well, you can compute Feynman diagrams to fix them. So this is the low energy, we just use the chiral Lagrangian. Now, at high energies, we have to use a partial wave expansion, and this is where things get complicated, because this spectral density will become a matrix. Because I was saying this system, for instance, is not positive on its own, it will receive contributions from off-diagonal terms in this matrix. And now the statement will be that the matrix that we'll construct, some rho j, will be a positive semi-definite matrix. Now, this will be the positivity constraint. That's the only one that survives a large n. But for full non-perturbative unitarity, you would also have the analog of the upper bound of this. But that we won't be concerned about that because a large n, that one doesn't play a role. Okay. So let me sketch relatively quickly how we do this. How we do this partial wave expansion. So here again, there's different ways to proceed. And the method that we will use was introduced in a different context in a paper last year by David, Simon Stuffin, Simon Canhuot, Julio Parra Martinez, and Yue Jolie, where they were studying at graviton, 4-point graviton scattering in higher dimensions. And the strategy is the following. So we expand, okay. In their case, they didn't have flavor dependence or a mixed correlator system, but we found that their method was the easiest to generalize to the case that we have at hand. So the general idea is that we want to expand the imaginary part of every of these amplitudes in a sum of our representations. So not just spin, but in this case also flavor representations that would be isospin, the analog of isospin expansion. So R, that will be representations of U and F, and J. And then we expand this, where we have some spectral density that depends on R and J, carries the S dependence, or the poles and so. And then we have some structure, group theory structure, that takes care of these representations, R and J. And the question is, how do I compute these guys over here? So if you only have external spinning states in 4 dimensions, I guess I forgot to mention that we are in d equals to 4. All the time. So you could use Wigner-D matrices. But there's another way, which is the one by the paper that I mentioned, where their insight was to realize that these structures could be obtained literally by gluing 3-point vertices. So you construct invariant tensors that represent the 3-point coupling of a pion or a photon in our case, with some intermediate particle x that is in the representation R and carries some spin j. And this will be represented by some invariant tensor generically denoted by this, which will have some isospin little group dependence that will carry this spin. Okay, these labels representations of the little groups, so we'll have some index for that, and then some index for the flavor representation. And then you construct these 3-point vertices, and then by gluing for the initial and final states, you can construct these structures. Okay, I know it's a little abstract, but I don't have time to give you details at this point. I am happy to elaborate later. Okay, so now what we have to do is label all these possible tensor structures, and we'll have some multiplicities. So we'll have many vertices. When you fix these representations, you'll have many multiplicities, and then what you have to do is glue all of them. So I and j, and this will make a matrix. And these multiplicities is what enlarges this into a matrix that's contracted here, and that's a matrix that will be positive semi-definite. Okay. All right, so I don't want to belabor on the details on how to construct these things, but what's very nice of this formalism is that it allows us to keep track of the quantum numbers of the particles that are being exchanged. And that's going to be useful for what I mentioned earlier, that were the large N selection rules. So the point is that there are some discrete symmetries in QCD that are parity and charge conjugation. So by studying the symmetry properties of these structures, you can keep track of the parity and charge conjugation of each of the states here. And here we start to see the spectrum of mesons of the real world. So not the spectrum, but the quantum. We see that we can capture the quantum numbers of the spectrum. So these particles here will be labeled by J, P, and C, and also their representation R. So we'll have the quantum numbers of what's being exchanged. And if you recall, this is how we label mesons that we measure in nature. Okay, so now in this way, you could construct the most general partial wave expansion, but we'll go beyond that, and we'll try to input at this stage that we have a large N theory. Okay, but with what we call the large N selection rules. So this is the generalization of Zweig's rule that I mentioned at the beginning, which is just a statement that mesons are QQ bar pure states. Okay, so a large N, there's no exotic meson. So all exotic mesons should be suppressed, and therefore we'll set their spectral density to 0, and we shouldn't even bother summing over this. So this, in a sense, is making some sort of spectral assumption that will be true for a large N. So that will be inputting more information into the system. Okay, so we find this condition gives us two sets of constraint or selection rules. One comes from flavor. And it's just a statement that these representations have to be only the adjoint of U and F. And the reason is clear because this guy is in the fundamental, anti-fundamental. So we have this furnished the adjoint representation of U and F. Okay, so all the other representations that you could sum here have 0 spectral density. So we can basically erase this thing and just sum over adjoint. So exchanges that are in the adjoint, because that will correspond to single meson states. And then the other condition or selection rules come from spin, and that's the statement that this spin of the particle should be the spin of a bound state. So since it's a QQ bar pair, this should be the product of orbital spin and orbital angular momentum. Okay, and now this becomes an undergrad quantum mechanics exercise or problem to work out what are the possible combinations of J parity and charge conjugation for such a bound state. And you see that not every combination is possible. In particular, you see that a GP JPC equals to these sectors, even plus minus, or odd minus plus, should be killed a large N. And these two statements is so that things that are not in the adjoint or things that are in this representation are suppressed at large N. It's just a statement that exotic mesons are suppressed at large N. And indeed, if you look at the meson tables, you see that exotic mesons of this kind are actually suppressed in experiment. So that's another instance of how, well, one of the arguments that people use to say that large N is not such a bad approximation of the real world. But in any case, this is the two things that we impose, and then we have this expansion for large N. Okay? So let me move on. We've done these two steps. We have a parameterization, low energy and high energy, and now we're ready to write down dispersion relations for each of these processes. Okay? So we have, for each of the amplitudes, we'll write down this, and we would like to write down something that has sufficient subtractions so that this is true. This is 0. So now what we have to discuss is the Regge behavior of each of these amplitudes to see how many subtractions these are the subtractions, how many subtractions we need so that this is 0, and we can write down dispersion relations. Okay? Yes?
Naive question. So if it was not the imaginary part, but the full amplitude, you would not be able to restrict to the a joint only, right?
That's a good question. I don't think you would. No, I think you can only do this for. So this is, I'm just killing the pole. I don't think I can kill the whole the full amplitude. Yes, but I haven't thought too much about it. So yeah, some thought would be needed. Thank you. Good point. Right. So the Reggie behavior of this thing. So Reggie behavior for QCD-like theories is controlled by Reggie theory. And we had a review earlier this week on Reggie theory. And if not, you can look at Zhao's lectures from 2018. That's where I learned it from. And the upshot of Reggie theory, that's the only thing that I'll need here, is that for a given amplitude m of SU, the behavior in the Reggie limit, where s goes to infinity and u is kept fixed, smaller than 0 in the physical region, this is controlled by the leading Reggie trajectory. So this grows like s to the alpha 0, 0 being the leading Reggie trajectory of u. Okay, so this we have some exchange. So we're looking at the Reggie limit growing in S, and then this is controlled by the Reggie trajectories in the cross channels. In the channel that we keep fixed, it's U for me. So we look at the Reggie trajectories in the U channel, and then the intercept, because we're interested in the forward limit. The intercept of these trajectories is what tells us the Reggie behavior, and that therefore tells us how many subtractions we can use for each of these guys. Okay. When you have external spinning states, there's some shifts because we stripped off some polarizations, and then this might receive some corrections. But the physics is that it's controlled by the intercept. You have to keep track of these shifts, but this is what the physics is. Okay. So what is this intercept? So here is where we can input another piece of information of QCD. So the expected Reggie trajectories, both from experiment and from lattice studies at large n, is something like this for the light mesons. I'm plotting J and m squared. And we have 1, 2, 3, and so on. So the leading Reggie trajectory is looks something like this, where here at 1 we have the rho meson. Here at 2 we have the F2, and then it continues on. And there's nothing above. At finite n there's the Pomeron, but that's a closed string, so it's not there at large n meson scattering. And then the leading intercept is this thing over here, which importantly, of the rho at 0, is below 1. So this is what I said before, that we managed to input this intercept by doing one subtracted dispersion relations. Okay? But now, there's the magic of this system, is that we don't have only one amplitude, we have a collection of them. So we can we can try to be clever and see, can I look for particular linear combinations of these guys such that they kill the leading Reggie trajectory? So now there's many quantum numbers, and not all of them. So yeah, if you study the symmetries of this guy, you'll see that not every sector, JPC more generally, is exchanged. So if you can cook up some combinations where this whole Reggie trajectory that has some quantum numbers is killed, then the Reggie behavior of that combination will be controlled by the subleading Reggie trajectory. And the subleading Reggie trajectory is that of the pion, which in the chiral limit lives here, pi. So it has exactly 0 intercept. And okay, it looks approximately parallel, but we don't really know if in the large n limit at infinity, well, it looks approximately linear and parallel. We don't know all the details, but all we need is the fact that it crosses at 0, and that we know because we're in the chiral. This is a Goldstone boson, so it's massless. Now we're expanding around u smaller than 0, and then approaching 0 from the left. So that means that we are allowed to take one more step of Reggie behavior. So this thing will be alpha of the pion at 0 equals 0. So that means that for some particular combinations, we obtain improved Reggie channels where we can take one step better Reggie behavior. And that would allow us to capture coefficients that were too low in derivatives that we could not capture before. Okay? Yes. So that's one of the main points that we obtain with this system. Okay? So are there any questions at this point? Okay, so yeah, let me get to results. Now the machinery is the same. We write down dispersion relations, obtain some rules, null constraints, and we can make plots like those. And we have many plots like those over there. And I just want to show you one that I really like and discuss why I like it. So okay. So the plot that I like is one. The details are not important, but it's one where I'm plotting some two-dimensional section of this infinite dimensional parameter space where I have some order 2 couplings, meaning order 4 in derivatives, of the some point coupling, 4-point couplings that appear in the 2 pi 2 gamma system. Okay, I can give you the details later if you want. And then there's another one that's independent I call prime 2 pi 2 gamma. Okay, so it's qualitatively analog, the analog of this. Oh, and also they're suitably normalized. Okay, that's what the tilde means. And what we find in this one is something that looks sort of like this, a diagonal line that crosses 0 that I didn't draw very well, but anyways. And then some particles over here. This is straight, and this is straight over here. Yeah, and that's it. So we find this region, and it actually converges very quickly of sharp corners and lines. And so let me explain you why I find it interesting. Well, the reason is because this line over here is due, so this line over here is due to the large N selection rules. And we know this because I did erase it. So if we include the exotic mesons, then what we find is a bigger plot that looks rectangular like this. But if we kill this, if we make this assumption of large N and we kill these exotic mesons, then the plot shrinks to this slanted line over here. Okay, so this line is really a consequence of this generalization of Zweig's rule. Okay, well, why is that interesting? Well, because you can start looking at these corners and think what are the theories that saturate these corners. Okay, and it's very hard in general to guess. But for instance, we saw here that this line over here was saturated by a spin 1 Regge particle. Let me say that again. A spin 1 exchange. Okay. A spin 1 exchange does not satisfy the spin 1 Regge behavior on its own, but it can be suitably UV completed by masses at infinity, at least in this case. So you can look here, see what are the possible spin 1 particles in the spectrum, and you find that there's 3 of them. There's the 1 plus minus, the 1 minus minus, and the 1 plus plus, where I'm saying J, P, C. These are different mesons. This is the rho. And the other one are the A1 and B1, I don't remember which is which. But these are 3 particles that could possibly be UV completed in a manner analogous to that one to explain some of these corners over here. If you do that analysis, okay, we haven't found the UV completion, but you can do the simplest thing and see where would it lie. And I just plot these values for these exchanges. And what I find is that this point over here is the 1 plus minus exchange. This point over here is the 1 minus minus, the rho. And the other one is outside the bounds. It's this guy over here, 1 plus plus. So 1 plus plus, if I didn't have the it's a shame I erased it. But if I didn't have the large N selection rules, would be allowed. But as soon as I turn on, so okay, what do I mean by would be allowed? So let me try to clarify. These amplitudes are not allowed on their own, but there's hope that they may be able to be UV completed in a funny way at infinity, so that these are just simple solutions to crossing that saturate my bounds. Now, this seems to be possible for these 2 guys, because then they're in the allowed region, but it looks like this is not possible for this guy. And the reason seems to be that the UV completion, so yes, you have to add masses at infinity, but you would need exotic mesons to do that. You need masses that are in the quantum numbers that are forbidden at large N. So when you include that, you see that this funny solution to crossing is killed, and we push the bounds farther into something that we have no idea what it is. I don't think it's QCD, but it seems to have to start to have more information of the large N assumption. So that's why I like this thing a lot, because with these new assumptions, we're going beyond simple solutions to crossing. And now the question is, how can we do the same or something similar for these guys over here? How can we go beyond that? And this brings me to another thing that I advertised at the beginning, which are the Goldstone constraints. So the Goldstone constraints are the generalization of the Adler zero. Remember, that was the fact that these are Goldstone, that is Goldstone scattering of massless particles, and we want to impose these are Goldstone bosons. So the one that could be used to rule in these corners, rule out these corners over here, is one that appears at order p squared in the 2 pi 2 gamma system, right? Because these are things from the 2 pi 2 gamma system. So at order p squared, you can write 2 local terms of 2 pions and 2 photons, pi A, pi B, and then you can have 2 different flavor structures. You could have the trace of q squared of TA, TB, where these are just the generators of the algebra, trace of q, TA, QTP. Okay. So in principle, there's two independent terms, this with this or that flavor structure, and that means that you would have two independent coefficients at this order p squared. But if you examine carefully this system over here, where we've written things in terms of this U of the nonlinear sigma model, you see there's two terms at this order, but when you expand it in pions and photons, you see that both of them contribute to a very specific linear combination of these two. So in principle, there's two independent ones, but when you look at it carefully, there's only one combination appears. They're not independent. Okay, so that means that two a priori independent coefficients should be equated. And if you do that carefully for these two putative theories, they don't satisfy this constraint. So that means that in principle, by imposing this Goldstone constraint, like something like some G1 in some sector A has to be equal to some G1 in some sector B. If you impose that, you would be able to kill these corners. So we got very excited, we put that into the computer, and we found the same plot. What's going on? So then, after thinking a lot about it, it turns out that SDPP is throwing away this constraint. So it seems to be some numerical abstraction. We have some intuition for what, I'll say it in a second, but it seems to be that this is a valid constraint that would kill these things, but SDPP doesn't like it, and it doesn't input it, so it's just ignoring it. And the reason seems to be that there are null constraints oscillate in spin. So we have contributions that are very large with positive spin and very negative, so large and negative with negative spin. So then when you do when you run SDPP positivity bounds in the way we truncate null constraints, these are set to 0. SDPP just weights them by 0. Yeah, even and odd, yeah. Okay. So there's contributions from even an odd spin with opposite sign. So yeah, in the end is that it looks like this is some abstraction and maybe suggests that we need some to rethink how we're inputting these null constraints. And yeah, we welcome ideas on how to circumvent that issue because yeah, perhaps we need some resummation of the null constraints so that they can probe these sort of constraints. And we actually don't find just this here, even with the improved Regge behavior that we find external constraints from crossing and so on. We also find this feature that there seems to be some numerical abstraction that's not being taken into account. So yeah, that would be a very nice direction to make progress, because that would get us closer to some theory of interest, perhaps QCD. And then the last thing I want to discuss is the anomaly, which is the one that I started with. So right. By doing the same sort of bounds for this coupling here, bichiral, we can obtain the following bound. We can obtain suitably normalized bichiral. That would be this ratio of bichiral over absolute value over G1 from the 4-pion system, G2 some coupling of the 2-pi to gamma system. So this goes back to Slava's question. You need this sort of normalization to cancel out this bound has to be doubly homogeneous, and that's why we need two normalizations to cancel out the normalization of the pion and the photon. And for this, we find some numerical bound that's not particularly telling, something like 10.58. Okay. And then the order, this is dimensionless, that's why there's no powers of the mass, but more generally you need powers of the mass. So, okay, well so this is not just the bound that we can get, but as I had advertised before, it actually couples to this system, to this section here. So we can rerun that bound at every point of this 2D space. And then this builds a three-dimensional plot that my drawing skills do not allow to reproduce, but I'll try to just distribute what happens. So what happens in this bound is that it's maximized on this straight line here. So this goes up to 10.58, and it's saturated all along this line that was what we call the Skirm line. And then it goes monotonically down. So here it's a little lower, and then it goes down to 0 at this corner over here. Okay, and then we're trying. It's still not clear exactly what things are saturating these bounds. And in fact, what we thought was understood now that this line over here corresponds to just the spin 1 particle. If we look up in this third direction, we see that just the rho exchange doesn't saturate the bound. So that means that there might be something more rich going on, where there's particles that decouple from pure pion scattering, but that couple to the pion photon system, and that saturate that bound. So there's still things that have to be understood there. And then the last thing why this bound is nice is that we can remember that this is actually matched so this is actually fixed by anomaly matching, right? So remember that that was proportional to k, and we set k equals to n, so we can put some fixed number, b chiral equals to some fixed number that we know times n. So then we can reinterpret this bound as something like this. That's some square root of g 2 pi 2 gamma. So this guy over here over e squared that comes from this fixed number here is greater or equal to some fixed number that depends on these and some other factors times n over f pi squared. So that's nice because this is something that we could read off from the lattice and plug here to find a numerical, a bound that's true in the large n limit for this particular coupling on 2 pi 2 gamma. And just for amusement, you can plug n equals to 3 if you wish, and then you get some number in terms of GV, 2.262 GV, where I've also put this, the value of this in the real world, and it would be great to compare this to experiment. Now, while this process, 2 pi into 2 photons, has clearly been studied in the lab, this is too high order. So this is order 2, meaning order 4 in derivatives. So yeah, I didn't even write it here. It's it's hidden in these dots, and those are not measured in experiment because you have to do matching with chiral perturbation theory, and the only ones that we have been able to find results for are these guys here. Now, these guys here are what I would call some G1 2 pi 2 gamma, and we do have some rules for these guys, but unfortunately, again, they decouple from all our bounds. And that brings me to the last point that I want to discuss. That's the other obstruction that we have encountered. So we have all these we've pushed forward all these constraints from QCD that we want to input into the Bootstrap, but we found some numerical obstruction. There was these oscillations in spin that I briefly mentioned. And then another issue is that many coupling, well, not many, 3 couplings that are very interesting because they're low in derivatives, like E squared, the gauge coupling itself, this guy here, and A chiral squared that I mentioned before. We have some rules for these guys, but they decouple from positivity bounds. And the reason seems to be, the reason is that these guys are at lowest derivative order, and that means that they have to be used in normalization. So you need to put them downstairs. The reason is because they decay the most slowly in the mass, and then theories that only have masses at infinity, if you put them upstairs, would make the bounds diverge. Okay? I know this was a bit fast, but the point is that you have to put them downstairs, meaning use them as normalization. But you can only do that if there's some rules are explicitly positive definite, or yes, positive semi-definite. But for all of these guys, we find that there are some rules. The some rules that we find are not positive semi-definite, even though we know that this thing has to be positive. We also know that this thing has to be positive. We're not so sure about this one. But it would be great if we found positive sum rules for these things, because if we did, then they would couple to positivity bounds, and we'll be able to put bounds for these guys. Okay, so let me quickly mention why they would be interesting. So this one is measured in experiment, and we could compare to experiment. This guy here is also matched is fixed by matching the anomaly, and that would allow us to put more bounds where we have this independence. And the one that I think is most promising is this one over here, because if we manage to couple this into positivity bounds, and we'll use this as normalization, we could use, for instance, instead of this, we could make another bound that looks like this, but where this is replaced by E squared. And then this bound over here would just be E squared, which would be order 1, would be just 1. And then we'd be able to put this bound that I mentioned in the beginning on the scaling of f pi squared with n, which is the thing that's measured in the lattice. So it'd be great to compare this with lattice results at large n, because, well, it's very physically meaningful. Okay, and we're not sure how to obtain these positive sum rules, but there's clearly many things that can be done. So what we did, if you remember, I've erased everything, was to restrict to the simplest case where we just had electromagnetic currents. So we restricted to this U1 subgroup of the UNF, but more generally we could consider any A left and A right background gauge fields. So we could redo rerun this problem by using more general backgrounds and obtain new sum rules for these guys. Then another thing that we could do that I briefly mentioned before is take the electromagnetic currents of shells. So we were using photons as avatars for this thing, but they could be taken off shell. We didn't do that. If you did that, again, you would obtain more sum rules and null constraints. And there's room for hope. It's not guaranteed, but there's room for hope that some of these new some rules will be positive or linear combinations are off, and then they will make these things coupled to our bounds. Okay, so I'll leave it at that. I hope I've conveyed our enthusiasm for this problem, and we clearly welcome ideas on how to solve all these issues. Thank you.
Do your bounds depend on the choice of the Q matrix?
They do not. So when we strip off the flavor dependence, all of them are proportional to some trace of Q and generators. So the Q is always stripped off together, and then nothing depends on it. Sure, if your Q matrix is a particular one, some of the processes might be 0, but what we think is that you can probe all the possible Qs so that all those terms are probed. Yes, and then the dependence drops out as long. So the only thing we assume is that it's diagonal, and there's some things that commute those we kill. So more generally, if you take general non-abelian backgrounds, then you would have new constraints that might give new sum rules. Thanks.
Hi, I didn't quite understand this point about u goes to 0. So you have this pion pole, so it's basically a constant, right, at large energy. But you said you were going from below, so the Regge trajectory is okay, so a bit negative. So I didn't quite understand that. So because if it's just a constant, then you can't drop the arc at infinity, right? Like you want it to be like it goes like s to the 0, right? Because its intercept is 0.
Right.
In the forward limit, yeah?
Yeah, so if I understand the question, it's about dispersion relations, right? Whether we can, so ds at infinity over s, m of s, u, s to the k. So if you have spin 1 Regge behavior, k has to be 1. If you have spin 0 Regge behavior, then you can take this thing. So that means it grows like, yeah. So okay, we're doing things at u smaller or equal than 0, and what we have from this Regge and
no, so that I understand. I meant, so you're doing it not at u equals 0. You're actually at u equals negative. That was the question.
So the logic is as follows. So we're doing things at u smaller than 0, and then we write down dispersion relations at fix u smaller or equal than 0, and then we do an expansion around the forward limit. So we'll have derivatives in u, but you're approaching them from the left. So the idea is you write down this dispersion relation at fixed negative u, but it's abstract. You don't have to plug it in, and then you expand around u, approaching 0 from the left, and then that's how you. So in the end, we're doing forward limit, but the step of doing dispersion relations, we're always below 0. That's why we can do these subtractions. Thank you.
Sorry, maybe I misunderstood or missed it. Your original bound, which you found in the previous paper, was it somehow improved by adding these new constraints?
Very good question. So yes and no. So mostly what we did was to extend the parameter space. So first we only had couplings that appear in pure pion scattering. Now our infinite dimensional space of EFTs has been enlarged by these other things. So at first it was like, oh, that's sad because we only put bounds on new couplings, but these couplings are actually physically meaningful as well, and they actually capture mesons in the spectrum that completely decouple from these. So the answer is yes and no in the sense that we've extended this direction, and if we manage to, fix some slice, so this is like you can think of it as a pyramid or something like that, so something that extends and that's not straight. So if we could fix some slice in this plane, these bands would shrink. But of course, while we can fix the anomaly, we don't know the value of these couplings over here. So we know this thing from the UV, but this thing still depends on experiment. So no, we have not, our bands have not improved, but we've understood a lot better this parameter space.
Thank you.
Right, and Leonardo's comment is that if we could fix f pi, then this ratio we would know it would be a number for QCD, and then we could take that slice and the bands would improve. Thanks.
So are there any prospects for comparing with large N lattice results?
Right, yes. So The issue is that both experiment and lattice, they probe or they compute or measure the lowest couplings. And the lowest couplings is the ones that we always have trouble with because we need a minimum number of subtractions. So for instance, this G2 and G2 prime have not been measured in the lattice and the large unlimit, but I heard that there are some groups that are actually computing these things right now. So that would be great to compare to these couplings. But then the one that would be very interesting, so one possibility is that they move up in derivatives so that they compute these couplings. The other one is that we move down in derivatives and we probe these couplings over here. So the one that I think, well, the one that certainly our results is the ratio of these two things, and it would be very nice if we could go down to that one and measure to that compare to that very well measured result.
Thanks.
So I have two questions. One is I didn't understand the motivation to go off shell. What do you expect to improve when you send the photons off shell?
What do I expect from that? Right. So now you have more kinematic variables, not just as in U, but you also have p squared of each of those. So you could think of the behavior as you send that to infinity. You could write down dispersion relations with these extra kinematic variables. So that would the whole processes would still be described by the same Wilson coefficients. So that that could help you obtain new sum rules and null constraints for the same couplings. So in that sense, the important point is that we're not just considering a bigger system with when we enlarge this farther. This is basically all there is. Now all these other new directions are new constraints for the same coefficients, and that's why it's very interesting because we could combine them with the null. You just have to give me one sum rule, tell me that's true, and then I just input it into my problem. I don't care where you obtained it, and then that could push things farther.
Okay, so it's generic. You don't have a sharp idea of.
No, we haven't thought too much in that direction yet.
And my second question was about. Do you think it would be useful to also combine this with, say, this dilaton probes that would give you access to the A anomaly, so that you would have another handle on the number of degrees of freedom in the UV?
I think it would be extremely useful, extremely nice. Yes, because if we could say bound some ratio of the chiral anomaly and the A anomaly, that both can be computed in the UV, that would be perhaps, if we can dream, we can dream of obtaining some ratio that we can fix exactly from the UV Lagrangian. If we could do that, of course, like any bound that involves that will allow us to shrink our plots farther into something that really depends on QCD. But it's hard. I mean, there's many things involved, and as you see, always you have to normalize by many things. So one of the things you would have to normalize by are, for instance, the mass of masses of the internal states, or like there's many things that will come into the game. So it's hard for me to say whether just including external probe dilatons will give you sharp bounds, but it's certainly something that one should think about.
Can you say a bit more, like explain the logic about putting bounds on E? Because E was an infinitesimal, was basically, your photon was a probe photon, was non-dynamical field. So, I mean, I can understand that if you, for example, just say, well, does my theory have electromagnetic current? Okay, this is supposed to put some constraints on the theory. But you cannot expect to put a bound on the electromagnetic coupling. I mean, it just sounds weird. I mean, it can be arbitrarily small.
Yes.
Yeah. So without including fully electromagnetic field as a dynamical field in your Lagrangian, which is what you are not doing. So is it just a choice of language, or? Yeah.
Probably. Yeah. So you wouldn't be putting a bound on E like absolute gauge coupling. I totally agree with you. All our bounds. All our bounds cancel the. Okay. So when I say that we have a sum rule for E squared, you should think something like this at low energies equals to some high energy average. This is the same as having a sum rule for this guy over here. So this F pi is the normalization of the pion, E is the normalization of the photon. So we also have a sum rule for F pi equals to something. Now, of course, this thing hides. Okay, these things are homogeneous. So this thing has the spectral density here, and it also has the spectral density there. So the only thing that we can put bounds on are different ratios. So so here, if we have maybe I didn't explain this properly. What we would not put a bound on E, but when you match the anomaly, this thing also has some power of E because it comes from three pions, one photon interaction, and then what you get is this ratio of this coupling with E. So we managed to do that in terms of E. You would see that E cancels out. So we never will put a bound on E. It's just something intermediate that we use to put bounds on other things.
Okay.
We can chat more later.
Very good. So let's thank Jan.
Thank you.
Yeah, and let's continue next week. Yeah.